In this lesson, we're going to learn about balancing redox equations. So these actually are a little bit different than what we've seen before because there's a little bit more to consider. No longer are we just looking at atoms and whether or not they have the same number of atoms on each side of the equation, but also the way that they exchange electrons and the number of electrons that are exchanged are legitimate. So what we do here is that when it comes down to it, we want to use the half reaction method. The half reaction is something we'll address in a second, but as you can imagine, it's the half of the overall reaction. So this is a prompt that we'll start off with Ce4 plus AQ and SN2 plus yields Ce3 plus and SN4 plus. So superficially, it kind of looks like they're balanced anyway, right? Because don't you have just Ce, which is cerium, and then Sn, which is tin? Don't you have one of each on each side? So doesn't that really balance out? Well, if you notice, the charges aren't really, accurate in terms of balancing out because they aren't, reflecting the number of electrons that have been exchanged. So this right now, even though, again, the atoms might work, the number of electrons that are exchanged don't quite work out. So that's why this is considered to be unbalanced. So let's talk about how we actually balance it. And this is going to be a general method, which we'll go back and balance that prompt I just gave you a second ago. So first of all, we're going to have to write out the two half reactions, which we'll get to in just a moment. And then from there, you have this whole procedure, which is written out here. And what I'd rather you do, instead of just kind of going over this method, I'm going to talk about how to work this out. So I've recreated that chart here, or that little steps of the procedures, by kind of copying and pasting up here at the right. And then I'm going to use this prompt here to balance, to kind of see how it works. So first of all, the two half reactions. The two half reactions, just kind of looking at what happens here. You're really looking at the two substances that are going to be sort of the change from the left side to the right side. So cerium appears on both sides, and then tin, right, this goes from here to here. And since those are the substances, like the actual atoms, the actual elements that are changing, we're going to consider those to be part of the same half reaction. So let's break this down. The first one, let's do this in black. This is going to be Ce4 plus. For the sake of also simplifying your work, you can kind of disregard the states of matter for now. That to be added in later on. But Ce4 plus is going to yield Ce3 plus. Right, that's going to be the black. And then in red, I'm going to do it kind of underneath it because I'm going to have to make some edits here. I'm going to do this in red. Is going to be SN2 plus is going to yield SN4 plus. So let's go and do these one at a time. So for each half reaction, let's balance each half reaction separately. First, we're going to balance the major atoms. So basically, what are your major atoms? Are the non-hydrogen, non-oxygen atoms. Those we'll deal with later on. So with Ce and Ce, there's the same number of atoms, right? That part's legitimate. Then the next bit is balancing the O's and the H's. Well, again, right now we don't have any O's and H's, so those parts we can kind of disregard for now. But we do need to figure out total charge. So the total charge here on the left side is +4. On the right side is +3. So now we got to figure out what side do we add electrons to reflect the change that would go from 4 plus to 3 plus. Well, again, going from 4 plus to 3 plus, right, the charge seems to have gone less positive, right? It goes from 4 to 3. And so what's going to cause that is that you're going to have to add electrons to the left side to make that happen. So the easiest way to think of it is basically adding negative electrons. Which side do you have to add it to make it so it's overall neutral? And since -1 is over here, and then a +4 right there, so what's -1 plus +4 is +3, and that matches the +3 that's right there. So overall, right now, we have a balanced half reaction. Now we have to do the same thing for the red now, so that's your tin. So looking at tin, again, the major atoms, Sn and Sn, right? There's only one of each, so that's fine. O's and H's aren't really a part of the conversation because, there aren't any O's and H's to worry about right now. So then we look at the total charge, right? I have +2 on the left side, +4 on the right side. So where do I add electrons so that I can make this overall the same charge on both sides? Well, if I notice that it's +2 here, +4 then, you're going to want to add 2 negatives to it to make sure that they, again, overall will match the charges over here. So we're not talking about canceling charges out necessarily. We're just talking about making sure that they match on either side of the equation. So we have 2 right here, 2 minus. Combine it with the +4. That's going to be overall +2, which matches the +2 that's over there. So that takes care of basically step 1 and 2. So that part and that part are taken care of. Let's talk about step number 3, which is to find the least common multiple for the total number of electrons. Well, electrons are right on the left side of this first one is just 1. It's 2 here, right? So what do I distribute? I can distribute a 2 throughout the entirety of this top one. so that it ends up having the same number of electrons. Because remember, in redox reactions, there has to be the same number of electrons given up as there are accepted, right? That's that law of conservation of mass. In the same way here, law of conservation of electrons. So we make sure that both sides have the same, or both equations, both these half reactions, result in the same number of electrons that are being exchanged. So as a result, then I can distribute it 2. So I'm going to rewrite this where it looks like, use them blue now, 2, 2, and 2. So that takes care of step number 3, right? So now we have, again, the least common multiple. So we have 2 as our least common multiple. So let's combine them now and then cancel repeated species. All right, so combining these, let's go and see what it looks like. I'm going to go ahead and draw a big ol', let's do this in blue actually. Let's go ahead and draw a big ol' equal sign, kind of like we're doing addition and subtraction. And there's a little plus sign, right? These little parentheses kind of separate it out so we know that's not involved in any way. And basically, you can write out whatever you see up there and cancel off what appears on both sides. So kind of looking ahead a little bit, I know that the 2e here, so this right here is on the left side of the equation. This 2e here is on the right side of the equation. Since they're identical in both identity and quantity, I know that the two effectively cancel each other out. So what we do instead is just go ahead and write in what's left over. This ends up being the 2ce, 4 plus, that was aqueous, right? We're including those, and SN2 plus, which is aqueous. And then we do we're going to do 2Ce3 plus, AQ, bring that down, and the SN4 plus that we had from before. And there you have it. That's how we balance this redox equation. So it talks about going through and identifying what it is that we have to balance, right? So we have the half reactions. We go ahead and balance each half reaction. We combine the two, and then effectively write the balanced equation out in the end. So now this is the balanced equation. This is what I'd want to see right here as a final answer, because that shows me that not only are the atoms balanced, right, the number of each atom, but also the number of electrons that are there are balanced as well. Now the electron part isn't as obvious because you have the electrons that we used as part of our balancing in the half reaction step, and those get canceled. So your final answer doesn't make it obvious that it's there, but that's kind of something that's understood. So now we're going to talk about redox specifically in an acidic environment. So this is again a reaction that occurs, or redox something that can occur in an acidic or a basic environment, and both of them are important. But we're going to start off by doing an acidic reaction because I think that's kind of our baseline, and then we'll talk about how to do a basic version later. So let's take a look at this one right here. This is a prompt you might see. The following reaction occurs in an acidic aqueous environment. And then we're going to have to balance the redox equation. So you see a bunch of stuff here, right? You obviously see a bunch of ions. And, so it's going to be a little bit of work here. It's not going to be as obvious as what we do with just regular balancing. One thing I want to mention too, it says commonly assume that all these redox reactions that we do, they're in net ionic equation form. So anything, that's like spectator ions, those are not included. All right, so let's go and take a look at this prompt. Let's go and identify again what our two half reactions are. That's our first step. Our first step, let's go ahead and see that this is MnO4 minus, and that's Fe. So I think it's probably going to be these two substances that are going to be somehow related to each other. So let's put those in a half reaction. And then over here, the Fe2 plus, Fe3 plus, right? These are kind of the same substance. So again, we'll try to make those a half reaction. All right, let's write those out. Let's go ahead and do the MnO4 first. MnO4 minus. Going to leave off the states of matter for the sake of simplicity. And I'm actually going to kind of leave a little bit of space here. Let me actually try this out instead. Let me rewrite it so it's MnO4 minus here. And then Mn2 plus here. Just to kind of condense it a little bit and sort of give us some more space that we can run on either side of this. All right, so I'm just going to do the first half reaction, and then in a second we'll do the second half reaction. So first, again, balance each half reaction separately by balancing the major atoms. All right, so let's see what major atoms we have. Again, anything that's not oxygen or hydrogen. Mn, there's one right here. Mn, there's one right there. So that's good. Now let's talk about balancing oxygen. So we know there's 4 of them right here. And it says to balance oxygens by adding H2O. Okay, so let's see. If we have 4 oxygens on this side, then I'm going to have to add 4 water molecules over here. Right? That's the rule. So right here, since that's 4 oxygens, that's going to match up with this. Well, some of you are probably like, wait, won't that end up messing with it by adding more H's? Yes, that is the case. But again, that's what the next step is for, is saying to balance out after the O's, to balance out the H's by adding either H plus or OH minus. So you have an option here, but since this prompt originally said that we're going to do this in an acidic environment, we're actually going to do H plus and ignore the OH minus. So let's go and balance this using the H pluses. So over here on the left side, I have 8 total oxygens, or sorry, excuse me, 8 total hydrogens. So over here, I'm going to add 8 hydrogens as well. So that takes care of balancing the atoms. Then we have to do the total charge by adding electrons. All right, so let's see how this works. Once more, let's go ahead and just add up the total charge on the left, add up the total charge on the right. So I have 8 plus, right, so plus 8 from this. I have a minus 1 from that, so that's a total of plus 7 on the left side. On the right side here, I have just a plus 2, right, so that's a plus 2 from that. There's 0 charge with water, so that's 0. So what do we have here? We have a plus 7 overall on the left side, so let me go and do this. We have a plus 7 overall. We have a plus 2 overall over here. So which side do we need to add electrons, and how many? Well, again, electrons are negative, and since I have a lot more positive on the left side, I'm going to need to bring that down a little bit by adding some electrons over here. But of course, I have to add the right number. So to go from positive 7 to positive 2, I'm going to add 5 electrons. So there's 5 electrons, right? That's in 5 negative, or minus 5. Combine it with plus 7. So negative 5. Combine it with plus 7, you get plus 2, which matches that over there. So we're set. So that balances out our first half reaction. Let's go and balance out our second half reaction. This time we're using iron, so it's going to be Fe2 plus, and that's going to become Fe. That's not an Fe. We're going to combine it with Fe3 plus. So again, let's walk through the process. Right, balance each half reaction by balancing the major atoms. Right, so Fe and Fe, those both, again, are the major atoms. No need to add any extra there. Adding O's and H's, well, there are no O's and H's involved here, so we don't have to worry about that. And then part D here, 2D, total charge by adding electrons. Well, again, the total left side is positive 2. Total right side is positive 3. So in order to add the appropriate number of electrons, I'm going to add it to the right side here. And how many? It's going to add 1, because positive 3 added to a negative 1 gives you the positive 2 total that's on the left side there. All right, so at this time, we've balanced out both of our half reactions. So step 3 now is to find the least common multiple for the total number of electrons. For the least common multiple here, we're going to compare 5 and 1. So what would I do to make sure we have a least common multiple? Is I'm going to distribute a 5 throughout the second half reaction, right? Because we want to make sure that the electrons, again, match, because the total number of electrons that's given up by one has to be the same amount of electrons gained by the other. And so we have to do 5. So I'm going to go ahead and edit this. So I have 5 here, 5 here, and 5 here. And then I combine. I'll do this in blue. Right, so once again, I add a little plus sign here, just to kind of remind me that I'm adding them all together. And let's go start adding stuff up. I do know, again, that this and this are both going to cancel each other out. You get same quantity and identity on both sides. And then we go ahead and write down everything else. So we have 8. That's not helpful. 8H plus. That's aqueous, right? We're talking about an acidic environment, so they're dissolved. MnO4 minus, aqueous. The 5Fe2 plus from this bottom equation, second half reaction. And then write down everything else that's over here. Mn2 plus, aqueous, plus 4 waters, which are liquid. And then the 5Fe3 pluses, that's all aqueous. And there we have it. That's how we have our balanced redox equation. Now, a couple things to kind of note here. First of all, this is acidic, meaning that we're going to see a bit of acid right there, right? Or at least that represents the acid, since H plus ions represent something from an acidic substance. And then also everything else is in place. So it's just one big balanced equation with a lot of parts that seemingly weren't there before, right? So where exactly did we get this H2O from and that kind of deal? So that part's not really important. It seems strange that they're all of a sudden showing up, but that's kind of something that's assumed. There's always going to be in a watery environment, and sometimes you produce water, sometimes you have to consume water in the reactions. But the important thing is that everything has balanced out, both in charge and in the element identities. All right, so let's go and give this one a shot. I'll give you a chance to try this one out. So please do, again, take a look at the procedures. All right, look at the substance you have and walk through that same process that we just did. One more here. This is another example. So this one, if you notice, it has a bunch of language here and kind of describes what happens. And then it tells you a bunch of information. But first of all, do note that it is all written out here. And this one does have a bit of information. So if you notice, there's an H2O here. There's also an H plus already included in there. And then notice that they ask you to, the prompt interview asks you to balance it. So what exactly goes on here? It's not really so much complicated because what this tells you is that that, first of all, with the H+, it tells you it's in an acidic environment, right? So that's a nice clue to have. But also the H2O and the H+, right, those you can kind of leave off to start because those are not important to the original half reaction, which goes down to the CRs that are involved. So go ahead and give this one a try as well. Again, there's some space here. I've recreated the little procedure here. But go ahead and give this a shot and try not to be too distracted by the H+ and the H2O. All right. So now we've done a bunch of acidic environment balancing. Let's go and do one that's in a basic environment. So if it occurs in a basic environment, here's the best procedure you want to follow. Essentially, you're going to balance it by doing it in an acidic environment first. So everything we've done so far has all been acidic environments. But then we're going to kind of finish it off and switch it to basic. So kind of going between acidic and basic, right? They're obviously very fundamentally different, but in terms of balancing them out, you can very quickly switch it back and forth between acidic and basic environments. So what we're going to do here is that, remember with the acidic environment, you should have a bunch of H+ ions floating around, but what we're going to do now is instead just add OH- to sort of flip it. So we're going to add enough OH- to neutralize the H+ in the acidic version so that we can flip it and make it basic. Let's go and see an example of how this might work. So in a previous example, this is one that we saw in the balanced equation. We were given this prompt earlier in a previous slide. And hopefully you would have found that the correct acidic environment balancing looks like this. So this is, again, what it looks like in an acidic environment. So this is, again, assuming you've done it like we said earlier. But, again, the prompt does ask you for a basic environment balancing redox equation. So this right here needs to turn basic. But first, we kind of take an acidic sort of detour, and then we'll turn it into a base after that. So again, notice that this is done basically. How do we know? This has been written acidically. You have the H+ right there. So having some H+ in solution, that makes it acidic. Let's turn to basic by adding an appropriate amount of hydroxides. So what is that going to look like? Well, again, I'm going to add enough OH- on both sides to neutralize the H, because I add it to both sides, first of all, because, again, if you add it to one side, it has to be on the other side, too. It has to make sure the law of conservation of mass is observed. But then how many? Well, since we have 14 H+, I'm also going to add 14 OH-, right? Because what happens when you add an OH- is that it combines the H+ to make water, make some new water, and therefore we want to make sure we add enough to completely cancel off all of those. And so over here, I'm also going to add 14 OH- to kind of balance that out. But of course, we can't just leave it there, right? If you have 14 OH- and 14 H+, what happens when you add these together? Well, it actually makes water, right? So let me rewrite that step over here, where it becomes Cr2O7 2-. I'm going to leave off the states of matter for now. This together now becomes 14 H2O, and you have 6 Cl- that we have from before. We're going to keep carrying out everything else that was there balanced as an acidic environment. Again, these haven't changed, so 3 Cl2, and then 7 H2O. And the 14 OH- that we added to the left side is also added to the right side, again, to balance out the states of matter, or to balance out the identities and the charges and such. And that's effectively it, except we have one more thing we need to consider. Don't forget, right, when we have things that are of the same identity on both sides of an equation, you can actually get rid of them. But of course, we can't completely get rid of these since there's only 14, or there's only 7 on the right side when there's 14 on the left side. So we just cancel as many as you can. And as you can imagine, all of these, again, will effectively cancel out. And this just becomes 7. So one more time to kind of recap what we did here. And this is not the entire final answer, but to kind of recap what we did here, right? We added some waters. We added some hydroxides, which kind of turn into water. And then that cancels off with the waters that were already there as part of the original balanced acidic equation. So let's go ahead and finish this off. I'll do this in another color. So we have Cr2O7 2-, that's aqueous. We have the remaining water that's left here, that's liquid. And we have 6 Cl-, that's aqueous. The 2Cr3+, that's aqueous. And the 3Cl2, that is a gas. And finally, right, we got rid of all the 7 H2Os, so we have the 14 OH- that's included as an aqueous substance. So that now is the balanced redox equation in a basic environment. All right, so big recap. All right, so you're given this prompt to start off at the top, so Cr2O7, yada, yada, yada. All this right here is your prompt. They ask it for a basic environment. But your first thing you want to do is first to balance it in an acidic environment and then flip it to being basic after that. And that's what we just did here by adding the appropriate number of hydroxides. So you end up canceling off all the H pluses. All right, you have one more example here. Go and give this one a shot. This one's a little bit more involved because you do have a little bit less to work with, but you do have to translate these into a normal equation first, and then go through the entire process. So first get it to the acidically balanced equation, and then flip it to basic. All right, that'll do it.